let's go ahead and get started. Let's start with this problem. So this problem says find n so that the error using either the trapezoid or the Simpsons method is less than 10 to the negative seventh for this integral, the integral from 4 to 9 of 8 times x minus 3 to the negative third. I suppose yours might be slightly different. And so then I've written up the trapezoid error formula. The error is less than or equal to b minus a cubed over 12n squared times the max of f double prime, the absolute value of f double prime. And for the Simpsons rule, it's the less than or equal to b minus a to the fifth over 180 n to the fourth times the max of the fourth derivative. And here are the derivatives of our functions. We have right, the function is 8 times x minus 3 to the negative third. The derivative is negative 24 times that to the negative fourth. The derivative of that is negative 4 times that, so 96 times x minus 3 to the negative fifth. The derivative of that's negative 480 times x minus 3 to the negative 6. And the derivative of that's 2080 times x minus 3 to the negative 7. So let's start with the trapezoid rule. So the trapezoid rule, I'm sitting down still. That's going to be less than or equal to, so b minus a cubed, 9 minus 4 is 5 cubed over 12 times n squared times the maximum f double prime. So here's f double prime, which, again, if I write it down here, f double prime of x is 96 over x minus 3 to the fifth value, to the fifth power. So can anybody tell me what value of x between 4 and 9, what value of x is going to make this as big as possible? Should I plug in x equal to 3? Well, I can't plug in 3. 3 is not an option. Should I plug in x equal to 4, 5, 6, something else, 9? What value of x, and you guys really should be able to tell me this, what value of x is going to make this quantity as large as possible?
Would it be 4?
It would definitely be 4, right? So the value that's going to make the denominator as small as possible. And usually, if people are trying to write a problem, it's not terrible. They're usually trying to make it so you can evaluate this somewhat easily. So if you plug in x equal to 4, f double prime of 4 is going to be just 96. Great. We want this to be less than or equal to 10 to the negative seventh. Okay. So then I'm going to erase these except for the fourth derivative, so I don't need these anymore. So then I have to solve this inequality. So I'm going to multiply both sides by n squared and both sides by 10 to the seventh. So on the left-hand side, I'm going to have, it's kind of going to be gross. It's going to be 96 divisible by 12. Yeah, 96 is 8 times 12. So 96 divided by 12 just gives you an 8. So over here we have, someone was very thoughtful when they were coming up with these numbers, because 5 cubed times 8 is exactly 1,000. 5 cubed is 125. 8 times 125 is 1,000. So you have 10 to the third times 10 to the seventh is less than or equal to n squared. That's 10 to the 10th. So n is bigger than or equal to the square root of 10 to the 10th. Square root of 10 to the 10th is 10 to the 5th. So n is bigger than or equal to 10 to the 5th. And this is exact. You shouldn't have to round up to the next one. So I believe so someone definitely, or some computer definitely was like, I'm going to make a nice question. The numbers come out super nice. So for this first part, using the trapezoid rule, n should be bigger than or equal to 10 to the fifth power. Yeah, that's kind of cool. It's nice when the numbers come out nice. So let's look at what happens when we do it with the Simpsons rule. I have to imagine it's not going to turn out to be as nice, but who knows? Maybe it will. So for Simpsons rule, we have that the error using Simpsons rule of absolute value is less than or equal to b minus a to the fifth over 180 times n to the fourth times the maximum of the fourth derivative. And that we want to be less than or equal to, again, 10 to the negative seventh, or 1 over 10 to the seventh. And here our fourth derivative is equal to 2,880 over x minus 3 to the seventh. Again, x is between 4 and 9. Again, we should plug in x equal to 4. So the fourth derivative evaluated at 4 is just going to be 2,880. And I kind of want to double check that because I did it in my head. And I feel like it's possible I made a mistake. So let me just double check real quick. I erased all my derivatives. So let me see. That'd be 8 times 3 times 4. So the first derivative is 3 times 4, then times 5, then times 6. Yep, 2,880. Okay, good. Good to be careful with your math. So then, that's going to be 2,880 right there. That's the maximum of f double prime. And then we're going to solve for n. So I've got 5 to the 5th over 180 times 2,880 times 10 to the 7th, right? Multiply this by 10 to the 7th is less than or equal to n to the 4th. So n should be bigger than or equal to the 4th root of this hot mess over here. I can cancel a 10 here and a 10 here. Let's just run 5 to the 5th times 2,880 times 10 to the 6th over 18. And then 18 will cancel. Let's see what we get. So 2,880 divided by 18 is 160. Yeah, that's a nice square number. No, it's not a square number, but it's looking pretty. It's looking like this is going to work out nicely. So let's see. So 160 times 5 to the 5th times wow, that's nice. That's 500,000 exactly times 10 to the 6th. Still feel like this isn't going to come out exactly right. So you have 5 times 10 to the 11th power, and then you want to take the 4th root of that. So here's what you get. You get n is bigger than or equal to 840.89. So let me ask you guys. Let me have everybody type it in the chat. You can type it to me privately if you want. You can type it publicly. What do I need to round up to?
The next even.
I think they didn't. No, that's fine.
Oh, I'm just
No, it's okay. It's totally cool. Exactly right. Since it's Simpsons method, we have to write the n is equal to 842. The next biggest even number. Yeah. So unless we made some dumb errors here, these should be the correct answers to this problem. I don't think I made any errors, but I've thought that before. I made errors. So yeah, it's always good to double check.
I was wondering, how did you get the max? Oh, it's the max of f double prime. What is that? What is
No,
that?
so it's the max of the 4th derivative. That's a 4. So when your derivatives get beyond 3, we typically write them as f superscript parentheses with whatever number of derivatives in there.
And why did you choose 4? F to the 4th power?
I didn't choose 4. I chose right the formula says right for Simpsons rule the error is less than or equal to b minus a to the 5th divided by 180 n to the 4th times the maximum of the absolute value of the 4th derivative. So I didn't choose it. The formula told us that's what we had to use. Can I clarify things?
Yeah.
Okay. So yeah, the trapezoid and Simpsons error formulas are just, here's the formula. Put all the things into it, figure out what the maximum of either the 2nd derivative is or the 4th derivative is, depending on the formula, and then go from there. Yeah. First one though, the trapezoid one was real nice. A little too tight here. So let's look at some improper. And I can't remember, have we talked about improper together yet? I don't think we have, but I can't recall. Yes, we have. No, we haven't. Anybody? It's okay if you don't know either. All right, well, hearing no one saying one thing or the other, let's go through the kind of usual stuff about improper integration. So improper integrals, yeah, I don't think, I know I talked about it in the other class, the 16th class I teach, but I don't think we've talked about it. So when you're trying to evaluate an improper integral, there are two different ways it can be improper. One of those ways is if one or both of your limits of integration are infinity. So for example, this, the integral from 1 to infinity of 1 over x dx, is probably the most common example of an improper integral. And the way we deal with it, whenever you have an infinity, is you always replace it with a variable and let that variable take the limit as that variable goes to infinity. And then I should say, not really a variable, but kind of a placeholder. So I'm going to rewrite this as the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. And then what we're going to do, we're just going to evaluate this integral like we usually would, with this limit just hanging out in front. That's going to be the limit as b goes to infinity of, well, we know how to integrate that. It's the natural log of the opposite value of x from 1 to b. We're going to plug in our limits of integration. B is positive, so I don't need the opposite value. So I'm just writing natural log of b minus natural log of 1. Natural log of 1 is 0. And as b goes to infinity, the natural log of b also gets infinitely large. So this ends up being infinity, which means the integral is divergent. Specifically here, we could say, although you don't really need to, I don't think, but you could say it diverges to infinity. So this particular function, 1 over x, so it's like this. Right, all this area here under the curve as you go further and further and further and further and further and further and further out has an infinite amount of area. So that's how you typically deal with an improper integral. You replace the limit of integration that's problematic with a placeholder, b or a, typically b for an upper one, a for a lower one. You can really use anything you want. Some books use t, some books use z, it doesn't really matter. And then you take the limit as that replacement thing goes to whatever thing you're replacing. Let's look at another example. Another kind of classic example. Let's look at the integral from 1 to infinity of 1 over x squared dx. Same idea. We're going to take the limit as b goes to infinity of the integral from 1 to b. I'd probably write this as x to the minus 2. Then we're going to integrate. So we're just leaving that limit out in front. The integral of x to the minus 2 is x to the minus 1 divided by minus 1 from 1 to b. I'd probably rewrite that. I prefer to divide my negative 1 the same as multiply by negative 1. So I'm saying the limit as b goes to infinity of negative x to the negative 1 is the same as 1 over x from 1 to b. When we plug in our limits of integration, we get the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. And unlike last time, where letting b go to infinity made the whole thing go to infinity, right? Because the natural log function, gets infinitely large as x gets infinitely large. This function does not. 1 over b gets infinitesimally small as b gets infinitely large. So this part here is going to go to 0, and you're going to be left with 0 minus minus 1, which is 1. So this integral, since when you take the limit of the integral from 1 to whatever, it equals a real finite number, this integral is said to converge. And it converges to 1. So if this limit exists and is real, the integral converges to that real number. If this limit doesn't exist, and infinity technically is a not existing, right? Infinity is not a real number. So this limit doesn't exist or is not equal to a real number, we say that the integral diverges. And if it's infinity, you can say it diverges to infinity or negative infinity, but sometimes the integral just doesn't exist. Or I would say sometimes the limit just doesn't exist. For example, what if I wanted to say, what's the integral from 0 to infinity of, yeah, why not? Cosine of 2x dx. All right, well, we know how to integrate that, but before we integrate, we need to write a limit. So it's the limit as b goes to infinity of the integral from 0 to b of cosine of 2x dx. And then we can integrate that. That's going to be the limit as b goes to infinity of the integral of cosine of 2x is 1/2 sine of 2x. From 0 to b. And then we plug in our limits of integration. So we still have, it's too bad that the limits of integration and limits are the same word, but it's just the way it is. So we plug in the limits of integration before we take the limit. We get the limit as b goes to infinity of 1/2 sine of 2b minus 1/2 sine of 2 times 0, which is 0. And sine of 0 itself is also 0. So now we're taking the limit as b goes to infinity of 1/2 sine of 2b. But that limit doesn't exist. The sine function, like the cosine function, oscillates up and down between between 1/2 and negative 1/2 in this case, forever and ever and ever. Right? I could draw it for you. I could draw some of it for you. Right? This sine function specifically, sine of 2b, has a period of pi and an amplitude of 1/2. So it does something like this. Sure. And it just keeps doing that forever and ever. So what's the limit? Well, this function doesn't get close to any one number, right? It just keeps bouncing back and forth, everything between negative 1/2 and 1/2. So the limit does not exist, which means this integral is divergent. Another way you could kind of think about it if you want to, if like this seems a little hand wavy to you, is you could say, well, the integral from 0 to, say, pi over 2 would be some positive number. And then the integral from 0 to pi would be 0. And then if we go to the next pi over 2, you get a positive number. And then if you go to 2 pi, you get 0. So every kind of other endpoint you pick, your integral values oscillate between some positive number, which I didn't calculate. It's probably like 1/2 or 1 or something. And then 0. And then whatever that positive number is, and 0, positive 0, positive 0. You keep going back and forth between these two numbers forever and ever and ever and ever. The integral doesn't converge, right? The limit doesn't exist. Yeah, we can look at that, but that's not super exciting. So notably, and this is important for our future kind of analysis of these types of integrals. Also, I don't know if you guys saw, I posted, did I post? I think I posted on Canvas, but my office hours are going to be over the summer. Now I'm not so sure if I actually did that. Let me double check.
Yes, it did. John.
Okay, good. So I'll be available over the summer, as will Grant and I think Sarah from 21C. So there'll be lots. Let me take a look here. Currently, over summer session 1, you can get help with 21C. Let me see here. From me, Tuesday, Thursdays, 9:30 to 11:30, and from Grant, Monday, Wednesday, Friday, 10 to 12, Tuesdays, 12:30 to 2, Thursdays, 1 to 3. So lots of help available, and that information will be available on the AATC website as well. So if you're taking 21C in spring and summer session 1, there'll be lots of places to get aid. Also, relatedly, there is not a co-21C class, a 21C co-class in fall quarter. Not that you couldn't get help during office hours in fall quarter, but there won't be a 21C co-class. So we saw that this integral diverged, and this integral converged. And it actually kind of, this is kind of an important thing to know, kind of when you have 1 over x to a power, when you get convergence and when you get divergence. And actually, I will say, so what we're talking about right now actually shows up a lot in 21C. So in 21C, you talk a lot about sequences and series. You talk about when a series, which is a sum, converges or diverges. And actually, one of the tests is what's called the integral test. And one of the tests is what's called the p test. And they're both related to what we're talking about here. We have 1 over x to a power, p, and you wonder when does it converge and when does it diverge? Or when does the integral converge or diverge? So the question is, when does the integral from 1 to infinity of 1 over x to the p converge or diverge? Well, we know how to integrate this as long as p isn't equal to 1. So if p is not equal to 1, which we don't have to worry about because we already know what happens when p is equal to 1, it diverges. So when p isn't equal to 1, we can just use the power rule. We can say, okay, this is, I have to write this here. This takes up a little bit of room. So let's actually write on the other side. This is important. You use this a lot. And actually, the reason this is really important is it helps us develop our intuition about other things. So, yeah. So the integral from 1 to infinity of x to the negative p, or 1 over x to the p. And again, p is not equal to 1. Well, great. We know how to do this. This is going to be limit as b goes to infinity of the integral from 1 to b of x to the minus p. And we're going to write that as the limit as b goes to infinity. Let's see, x to the minus p integral is going to be x to the negative p plus 1 divided by negative p plus 1. And I would probably like to rewrite this, from 1 to b. And yeah, I'm going to write this. So let's break this up into 2 cases. One case where negative p plus 1 is negative. Or another way you could say this is where p is greater than 1. So p is greater than 1. That means this power is negative, and I prefer for it to be positive. So I'm going to bring it down to the bottom. I'm going to rewrite this as the limit as b goes to infinity of, I'm going to write this as 1 minus p, 1 over 1 minus p, right? Negative p plus 1 is the same as 1 minus p, times x to the positive p minus 1. From 1 to b. Now I'm going to plug in b and plug in 1. So we have the limit as b goes to infinity of 1 over 1 minus p times b to the p minus 1 minus 1 over 1 minus p times 1. Okay. So now, as b goes to infinity, an infinitely large thing to a positive power, and p minus 1 is positive because p is bigger than 1, that's going to go to infinity, which means its fraction is going to go to 0 because you have 1 over an infinitely large thing. So this whole part goes to 0, and you get negative 1 over 1 minus p, or positive 1 over p minus 1. I don't really care what the number is actually. I just care that it converges. On the other hand, what if negative p plus 1 is bigger than 0? Or 1 is bigger than p, or p is less than 1? Okay, well, in that case, this power is positive. And so I'm just going to leave it on top. And this, the denominator is also positive. So I'm saying this is the limit as b goes to infinity of b to the negative p plus 1 over negative p plus 1 minus 1 to any power is 1 over negative p plus 1. But now look, b is going to infinity. It's raised to a positive power because that's positive. And infinity to a positive power is infinitely large. So this is going to go to infinity minus whatever, which is going to be divergent. So what we see is that this integral, 1 over x to the p dx, from 1, with the integral from 1 to infinity of 1 over x to p dx, diverges if p is less than 1, right? Diverges if p is less than 1. It also diverges if p is equal to 1, which we already showed. And it converges if p is greater than 1. This is useful because then you can basically say, well, if something looks like the power is big enough on the bottom, it's probably going to converge or diverge, depending on what we know. So let me show you an example. Basically, it's a helpful way of kind of developing intuition, specifically for improper integrals that have infinities in them, of whether or not things are going to converge or diverge. We'll do the integral from 2 to infinity of 3x squared over the square root of x cubed. Now we're still going to do the work because you can definitely do a u sub here. But here's what I can see. I essentially have an x squared on top. I essentially have an x cubed to the 1/2, which is an x to the 3/2 on the bottom. Yeah, that's interesting. So in fact, this one's real interesting. Here it looks like the numerator, right? Like overall, this is kind of like an x to the 1/2. It's definitely looking like things are going to be divergent. Let's actually do the work. So, yeah, so that seems, no, I guess that's totally right. Yeah, that's weird. Okay, so I'm pretty sure it's going to diverge because I have, I usually write this as a 1 over x to the negative 1/2, right? My p equal to negative 1/2 is definitely less than or equal to 1, which should indicate divergence. No, that's not exactly what we have, but it's giving us intuition about what's going to happen. So, let's do a u sub. I'm going to let u equal x cubed plus 1. Du is going to be 3x squared dx. I personally don't love changing my limits of integration when it's an improper integral. Oh, and I should actually back up, right? Technically, I should first, before I even do the u sub, I should rewrite this as the limit as b goes to infinity of the integral from 2 to b of 3x squared over the square root of x cubed plus 1. Now, you can either then write this as the limit as b goes to infinity of the integral from x equals 2 to x equals b, and do the u sub. Du is 3x squared dx, and the bottom is going to be the square root of u. Or if you wanted to, you actually could change the limits of integration. You can say the limit as b goes to infinity of the integral. Now, the person who wrote this, yeah, I don't know. I'm gonna say I don't think you should do it that way. The problem is, like, if I change the limits of integration here, I should then say, okay, the denominator is going to be 2 cubed plus 1, which is 9, and the numerator is going to be b cubed plus 1, which is kind of just not great. It's fine, but it's and you have the same thing here. So we'd integrate u to the negative 1/2. We're going to get the integral of u to the negative 1/2 is u to the 1/2 times 2. So 2 square roots of u from x equals 2 to x equals b. And then plugging back in what x is, we get the limit as b goes to infinity of 2 times the square root of x cubed plus 1 from 2 to b. Plugging in elements of integration, we get the limit as b goes to infinity of 2 times the square root of b cubed plus 1 minus 2 times the square root of 2 cubed plus 1. As b goes to infinity, b cubed goes to infinity, and the square root of that goes to infinity. So this goes to infinity. So this diverges to infinity. U substitutions can be kind of tricky when it comes to improper integrals. Let's look at another example. And I'll show you what I recommend if you think you have a u sub. So let's look at, say, the integral from negative infinity to, negative infinity to infinity of x cubed times e to the negative x to the 4th. Definitely going to be a u sub. So what I would recommend is actually doing the indefinite integral u sub before even dealing with any of this improper stuff. So off to the side here, like, okay, for the integral of x cubed e to the negative x to the 4th dx, we let u equal negative x to the 4th. Du is negative 4x cubed dx. So negative 1/4 du is equal to x cubed dx. Then my integral becomes negative 1/4 the integral of e to the u du, which is just negative 1/4 e to the u, which is just negative 1/4 e to the x to the 4th. Negative x to the 4th, sorry. I didn't write plus c because this is just my own work on this side. So then we can come back and deal with this. So to deal with this, when you have multiple problem points, right, both infinity and negative infinity are problematic, or more generally, right, if you have other problematic points, an integral can only deal with one problem point at a time. So if you have more than one, you have to break it up into enough integrals to have each integral having only one problem point. So if there are 2 problem points, you need 2 integrals. If there are 3 problem points, you need, right? Usually you only need to break up into 2, but occasionally you could have something with 3 problem points, which is a giant pain in the butt. An example of that would be like the integral from 0 to infinity of 1 over x natural log of x. This is the giant pain in the butt because 0 is a problem, 1's a problem, and infinity is a problem. So you have to break it up as the integral from like 0 to 1/2, and then 1/2 to 1, and then I have to break it up into 4 pieces, and then 1 to something, and then 2 to infinity. That's terrible, right? Because, so I know we haven't talked about it, but we're about to talk about how the problematic points for an improper integral are either the infinities or the places that make the function undefined. And here, 0 makes it undefined because you get division by 0, and also natural log of 0 is undefined. But 1 also makes it undefined because natural log of 1 is 0 and division by 0 is undefined. So yeah, this integral, hopefully no one would ever assign to you. It's actually probably not terrible in that, in fact, we'll probably do this one later because I'll show you that it's super easy. So keep it on the back burner. We'll do that one, even though it looks awful. So I'm going to write this as, I'm going to break it up into 2 pieces. The integral from negative infinity to pick any point you want between them. We usually pick 0 if we can. So we get those 2 intervals, from negative infinity to 0 of the function, and from 0 to infinity. And then we're going to write each of them as limits. So this one's the limit as a approaches negative infinity of x cubed e of the integral from a to 0 of x cubed e to the negative x to the 4th dx, plus the integral from, plus, it's a lot of writing, plus the limit as b goes to infinity of the integral from 0 to b of x cubed e to the negative x to the 4th dx. All right, so now, typically we deal with these one at a time. And the reason why is if one of them diverges, you're done. The whole thing diverges. So I never want to do both integrals at the same time because I don't want to do more than worse than I have to. So look at this first one. This one is equal to the limit as a goes to minus infinity of the integral of this, which we know is negative 1/4 e to the negative x to the 4th. Whereas I'm going to write negative 1 over 4 e to the x to the 4th. And now as from a to 0. And that's going to equal the limit as a goes to minus infinity of negative 1 over 4 e to the a to the 4th minus negative 1 over 4 e to the 0th. So as a goes to negative infinity, a to the 4th goes to positive infinity because it's an even power, and then e to the infinity also goes to infinity, which means having division by infinity is going to make this fraction go to 0. So we end up with positive 1/4 Okay. Now, since this one converged, we also have to deal with this one. So this one's going to be the limit as b goes to infinity. Again, we know that it's negative 1 over 4 e to the x to the 4th from 0 to b. And then we get the limit as b goes to infinity. I made a small mistake there. It's not huge, but it is a mistake. The mistake I made was that I plugged in the a first and the 0 second, and that is wrong. So this should have been slightly different. Let me just fix it because I think it changes the sign of our answer. Sorry about that. This should have been negative 1 over 4 e to the x 0 to the 4th minus negative 1 over 4 e to the a to the 4th. And this part goes to 0 because the denominator is huge. And this part's going to be negative 1 over 4. So we get negative 1/4, not positive 1/4. Okay. Here we plug in the top limit first. Negative 1 over 4 e to the b to the 4th minus negative 1 over 4 e to the 0 to the 4th. And b goes to infinity, so b to the 4th goes to infinity, so e to the infinity goes to infinity, and 1 over that goes to 0. So we get plus 1/4. So the whole thing converges to negative 1/4 plus 1/4, which is 0. And the reason it's 0 is because 1, it's convergent, but 2, it's an odd function from negative infinity to infinity. So if you have an odd function that converges from negative infinity to infinity, it's going to converge to 0. I should mention right? And so the reason this is working out here this way is because it kind of looks like this. Right, x cubed e to the negative x to the fourth kind of has this shape here. And so this positive area is the same as this negative area. And since they're both convergent, they cancel each other out. However, it's not always the case for odd functions. For example, this integral from negative infinity to infinity of, sure, x over x squared plus 1 is an odd function, diverges. In fact, we already have a good intuition it diverges because x over x squared acts like 1 over x. And we know that 1 over x is a divergent function, or the integral of 1 over x is divergent. So let's do the u sub. U is x squared plus 1. Du is 2x dx. Let's make our lives easy and just throw a 2 on there for the sake of it. So this is going to be, right, the integral of 2x over x squared plus 1 is just the integral of du over u, which is the natural log of the absolute value of u. Okay? So that's going to end up being, I got it. So we got to where we. So the problem is a lot of this is just the machinery, right? Like we can see it's going to be the natural log of x squared plus 1. We're going to plug this in to get infinity, but we still have to write like the limits and stuff. So this is going to be, and we have to break it up in 2 integrals. This is the integral from negative infinity to 0 of 2x over x squared plus 1 dx plus the integral from 0 to infinity of 2x over x squared plus 1 dx. Now let's just look at this half of it, because we know it's going to diverge. So the integral from 0 to infinity of 2x over x squared plus 1 equals the limit as b goes to infinity of the integral from 0 to b of 2x over x squared plus 1 dx. Now that's equal to the limit as b goes to infinity of, okay, the integral of 2x over x squared plus 1 is the natural log of x squared plus 1. From 0 to b, we plug in the b first, so we get the limit as b goes to infinity of the natural log of the absolute value of b squared plus 1 minus the natural log of the absolute value of 0 squared plus 1. But as b goes to infinity, b squared plus 1 goes to infinity, and the natural log of infinity goes to infinity. So this goes to infinity minus 0. So even though 2x over x squared plus 1 is an odd function, and we would think of the area on the right being positive balancing out the area on the left being negative, it doesn't count here, it doesn't work here, because the area on the right is infinity. And you can't say that infinity plus a negative infinity is necessarily equal to 0. So this integral diverges. And again, I want to point out, we didn't even do the other half of it. Once you know that part of an integral is divergent, you're done. The whole thing diverges, which is great. So the other type of integral that we have to deal with, that's funny. Sorry, I have to send this up in. I hadn't noticed before. Sorry, distracting. So that's one type of improper integral, where one or both of your limits of integration are infinity. The other type of improper integral is where you have a place where the function is undefined in your interval. So this integral from 1 to 3 of 1 over x dx is totally proper. There's nothing wrong with it. It's not, there's no infinities, and it's not undefined, or I should say it is well defined on the entire interval here. So this is a proper integral. this is improper. Because this function is undefined on the interval. In fact, let me show you. If you actually try to do this integral, so let me do a slightly different one to make it a little bit easier to see what I want to see. Let's say it's 1 over x squared. Get a little more interesting here. So 1 over x squared looks vaguely like this. And I'm going from -1 to +3. So I'm looking at all this area here. Okay. So let's try and do it the straight way, which is not going to work. I'm just going to start off by saying this integral is not equal to what I'm about to do. The integral of 1 over x to the second, or x to the -2, is x to the -1 over -1, which is -1 over x from 1 to 3. Plug in the 3 first, minus plug in the 1. So you get not what I was expecting to get. Yeah. So I was trying to make it more obvious that it doesn't actually work. Yeah. Oh, yeah. Okay, fine. Oh, sorry. That's a -1, not a 1. Apologies there. So that's a -1 over -1. So we get a -1/3 minus 1, which is -4/3. Which seems a little suspect because that area should be positive. It's definitely not. Well, I mean, the integral we got is definitely negative, and it definitely should be positive if it was going to be equal to that. So what's happening here is this is totally incorrect what we're doing, right? We can't just integrate this without paying attention to the fact that it's undefined at 0. So when you have a function, an integral, it's undefined at some point in its interval integration, you need that. If it's not already an endpoint, like if this was the integral from -1 to 0, great, we would just work on it. But if it's not an endpoint, you have to break it up. So we're going to break this up as the integral from -1 to 0 at the point where it's undefined. And then also plus the integral from 0 to 3, 1 over x squared dx. And now let's deal with one of these pieces. Again, I'm only going to start with one piece because I'm pretty confident it's going to diverge. Even if you think it converges, it still doesn't hurt to do it one piece at a time. So this piece here is going to equal the limit as a approaches 0 from the right-hand side. Why the right-hand side? Because we are between 0 and 3. And between 0 and 3 on the number line, if you're between 0 and 3, you're definitely on the right-hand side of 0. That's going to be the limit as a goes to 0 from the right of the integral from a to 3 of x to the -2nd, which is going to equal the limit as a goes to 0 from the right of -1 over x from a to 3. And then we're going to plug it in. We're going to get the limit as a goes to 0 from the right of -1/3 minus -1 over a. But then if you let a go to 0, you're going to get 1 divided by 0, which is undefined. So this is going to diverge. Right? This limit does not exist. It's either infinity or negative infinity. Specifically, it is positive infinity. So the integral diverges. So this. If you really wanted to, you could say it diverged to positive infinity by showing that both this part and this part both were positive infinity, because positive infinity plus positive infinity does still equal infinity. But if one was infinity and one was negative infinity, we would just say it diverged, and we wouldn't really be able to say anything else about that. Let's see what time is it. Okay, it's 3 o'clock. Got plenty of time. So let's look at some more examples of this type, and then we'll come back around to, yeah, we'll come back around to some of the questions you guys asked me, which are definitely more infinity ones. Let's look at something slightly less terrible than what I proposed before. Let's look at the integral from, the integral from 0 to 1 of 1 over x natural log of x dx. And again, I will emphasize here, this function is undefined at both endpoints. So an integral can only manage one problem at a time. So we have to break it up. You can break it up at any point in between the interval. Usually we kind of just split different. Here I would pick 1/2 for sure. So I'm gonna write this as the integral from 0 to 1/2 of 1 over x natural log of x dx plus the integral from 1/2 to 1 of 1 over x natural log of x dx. And I'm not really sure which of these might diverge, if any of them. Maybe they both converge. They probably don't both converge. One is probably diverges. But let's just try working with this one. So working with this one, we're going to rewrite that as the limit as b goes to 1 from the left. And for between 1/2 and 1, we are on the left side of 1. Basically, if it's an upper limit, you're approaching it from the left. If it's a lower limit, you're approaching it from the right. Integral from 1/2 to b of 1 over x natural log of x. Notably, we're going to have to do a u sub here. I don't like carrying all of this garbage with my u sub, so I'm going to do the indefinite integral off to the side. Integral of 1 over x natural log of x dx. U is natural log of x. Du is 1 over x dx. Great, that takes care of this. So I've got the integral of du over u, which is the natural log of the absolute value of u, which is the natural log of the absolute value of the natural log of x. So this is going to equal the limit as b goes to 1 from the left of the natural log of the absolute value of the natural log of x from 1/2 to b. Then we plug in our limits of integration. We get the limit as b goes to 1 from the left of the natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of 1/2. This part here doesn't matter. It's a constant. Natural log of 1/2 is some number. It's negative, but then it's the absolute value, so the natural log of the absolute value of that is some other constant. Natural log of b. Okay, so what's the natural log of b? It's 0. And then what's the natural log of 0? So it's really, for a lot of these problems, it's very important that you're aware of what the natural log graph looks like. Just a reminder, the natural log of x looks like this. It's got an x-intercept at 1, 0. But specifically here, as this is going to 0, this whole thing is going down to -infinity, right? For the natural log function, as the inputs get closer and closer to 0, the outputs get closer and closer and closer, or go get more and more and more negative. So this diverges. All right.
James,
Yes.
I have a quick question. So how come we chose our to separate the integral, the improper integral at 1/2?
Because we had to pick something between 0 and 1.
Oh, because
Arbitrary choice. You could have chosen 1/3. You could have chosen 2/5. You could have chosen literally any real number between 0 and 1.
oh, is it because 0 and 1 are basically make our integral 0, or like divide by 0?
Yes, right. The 0 and 1 make our function that we're integrating undefined. 0 because you get 1 over 0, and 1 because you get 1 over 0.
Yeah. Okay, that makes sense.
So wherever you have, if you have multiple places where the function's undefined, one integral can only handle one undefined place. So if there are multiple
Okay.
undefined places, you have to break it up into multiple intervals.
All right, that sounds good. Thank you, James.
Welcome. Let's look at a couple more examples. So if you had something similar but different, let's say that the limit, sorry, the integral from 1 to e of 1 over x times the square root of the natural log of x. Okay, let's actually, we know we're going to do, so I said e, gosh, I feel like lately I've been saying a lot of things and writing a lot of different things. 1 to e. So let's do the u sub. Now let's do the indefinite integral. Integral of 1 over x square root of natural log of x dx. We're going to let u equal the natural log of x. Du is going to be 1 over x dx. And then you're going to rewrite this as the integral of du over the square root of u, which is the integral of u to the negative 1/2 du, which is u to the positive 1/2 divided by 1/2, which is times 2. That's 2 square roots of u, which is the natural log of x. Okay, so back over here, this is going to be the limit. And so what's our problem point here? 1 is our problem point. As a, and you can use whatever limit you want. As a approaches 1 from the right, the integral from a to e of 1 over x times the square root of the natural log of x dx. And then we rewrite this as the limit as a goes to 1 from the right. We know what the integral of this is. It's 2 times the square root of the natural log of x from a to e. That's going to be the limit as a approaches 1 of 2 square root of the natural log of e minus 2 square root natural log of a. As a goes to 1, the natural log of a goes to 0. So you end up with 2 times the square root of 1 minus 2 times the square root of 0. So this one is equal to a real number, which means the integral converges. It converges to 2. Right, so if an integral converges, we usually try to say what it converges to. Right? Meaning, if you can find what the integral is equal to, you should say, oh, my integral converges to that value. However, sometimes we can't. What do I mean by this? I mean, sometimes you have integrals that you can't actually integrate, but you can tell whether they converge or diverge. Let's look at the this example. This one's not that hard to integrate, but fine. So let's look at the integral from 1 to infinity of x squared over x to the 6 plus 1 dx. This integral is integrable if you do a u sub where you let u equal x cubed. But I don't want to do that. I want to show you that I can see that this integral is convergent by doing the following. So first of all, notice that this function is non-negative. It's always greater than or equal to 0, no matter what value of x is. Specifically, no matter what value of x is between 1 and infinity. But then, x squared over x to the 6 plus 1 is less than x squared over x to the 6. Right? If the denominator gets smaller, the fraction gets larger. And that's equal to 1 over x to the 4th. And so if these inequalities are all true, it's also true that the integral of 0 from 1 to infinity, which is 0, is less than or equal to the integral from 1 to infinity of x squared over x to the 6 plus 1. It is less than the integral from 1 to infinity of 1 over x to the 4th. But here's the thing. This integral here, we know is convergent by the p-test, right? This looks like the integral from 1 to infinity of 1 over x to the p. And we said that this converges if p is larger than 1. Well, 4 is definitely larger than 1. So this converges. And since this is less than something that converges and still non-negative, it also converges. So we say this converges by comparison. That's kind of it, right? If you're positive and smaller than some positive thing that's convergent, you're also convergent. We could actually show it by doing the U sub here. It's not super hard to do, but I don't think we need to. Let me show you another example of using a comparison test. So here's a function that actually is impossible to integrate. E to the x over x. Definitely not an integrable function. Cannot anti-differentiate that no matter how long you spend. Here's what we do know. I know that e to the x over x is bigger than 1 over x, because I know that e to the x is always bigger than 1. At least, that's actually not entirely true. E to the x is bigger than 1 for x bigger than 0, which is fine because we are living in the land where x is between 1 and infinity. So we're set. So then we can say, well, if this is true, then this is true. But we know from work earlier today that this integral diverges, and it diverges to infinity. So this diverges to infinity, and this integral is bigger than that. If you're bigger than infinity, guess what? You're infinity too. So this also diverges to infinity by comparison. Kind of neat. So sometimes, and there's definitely, I was looking at the Schulten's homework, and definitely question 8, I really feel like is not a function we know how to integrate. So let me just show you guys. Question 8 on Schulten's homework is the integral from 2, or at least my version of question 8, is the integral from 2 to infinity of 1 over the square root of x cubed plus 6. So, yeah. So here's what I'm thinking. I have a square root of x. I have a 1. I'm going to ignore the 6 essentially. I have a 1 over the square root of x cubed, which is like a 1 over x to the 3 halves. And I know 1 over x to the 3 halves is convergent. I should say, I know that the integral of 1 over x to the 3 halves is convergent by this p-test kind of thing, right? This converges if that power is greater than 1. 3 halves is bigger than 1. So I know that this thing converges. And this is essentially the same as that. I mean, they're not exactly the same, but they're very, very close to being the same. They're similar enough that if this converges, this probably also converges. And here's how I can show it. It is definitely true that this function. So again, if you're trying to show convergence, you want it to be smaller than something that converges. If you want to show divergence, it needs to be bigger than something that diverges. This is definitely smaller than 1 over the square root of x cubed. Right? My denominator got smaller, my fraction got bigger. So this fraction is bigger than that fraction, but that fraction is equal to this fraction, or this expression. And then we can say that this integral is smaller than that integral, is smaller than that integral. I think from 2 to infinity. But this integral converges. So this integral converges by comparison because of the smallness of it converges. And I'm pretty confident, not 100% confident, but I'm fairly confident that this is not an integrable function. Like you cannot antidifferentiate. I'm not 100% sure, but I'm pretty sure that there's no way to find the antiderivative of that. Is doing a weird thing. So like you click these three, I don't know if I said this last week. I think you click these three buttons on my computer, Command Shift 4 to do a screenshot, and it gives you a little thing. But like when I'm doing it, it's taking like a good like 5 seconds before like it gives me the cursor to take the screenshot. It just seems strange. I don't know what that's about. So again, here's kind of the way we say this. So these are the comparison tests say basically, so if you have the following. So if 0 is less than or equal to the function f of x is less than or equal to the function g of x. If, so I should say given. So if the integral of f of x from a to infinity is divergent, then so is the thing that's bigger than it. Right? If you're bigger than something that diverges, you are also divergent. And also, if the bigger thing is convergent, then so does the other thing. So does the smaller thing. So if you're smaller than something that's convergent, you're also convergent. It can be a little bit tricky. So if I have something like this, yeah. This is when it gets a little bit trickier because e to the x over x squared, e to the x over x squared is bigger than 1 over x squared. But I know that that's not helpful because the integral of 1 over x squared from 1 to infinity, this is convergent, meaning that integral is finite. Well, that means this is bigger than a finite number. Let's say I'm pretty sure this is actually equal to 1. So here's what we've said. We've said this is bigger than 1. Well, great. That doesn't really tell me that much. If I'm bigger than 1, well, I could be 2, and I could be convergent, or it could be infinity, and it could be divergent. I don't actually know. So this isn't super helpful. So showing that something's bigger than a convergent integral doesn't really help us. So in this case, what we need to do is we need to say, well, it's also true that e to the x is bigger than x. Right? If you think about the graphs, e to the x looks like this, and x looks like that. E to the x is definitely always bigger than x. And then e to the x divided by x squared is bigger than x divided by x squared, which is equal to 1 over x. So it is true that the integral from 1 to infinity of e to the x over x squared dx is bigger than the integral from 1 to infinity of 1 over x dx. And that is divergent. So that's divergent. So that's a real quick breakdown of the convergence tests. Sorry, the comparison tests for convergence and divergence. Sure. Yeah, I feel like there's also a limit comparison test, but I feel like that might not be really what we need to talk about. If that's not true, like, so if you guys talk about the limit comparison test in class tomorrow, let me know and we'll talk about it on Thursday. But I think we should spend some of our time. Oh, I still have these other. So let's go back to the other types because there were definitely a few questions that were asked that seemed kind of tough. So let's look at, oh yeah, this is a classic. I think it's a classic anyway. I'm going to change it. I'm going to change it just a tiny bit. So this is very similar to one of the Morris questions. Where'd you go, Morris questions? This is very similar to the fourth Morris question. I'm just going to change my numbers slightly. Let's do the integral from, didn't even think about that. Oh no, that's fine. That's actually, okay, that's not so bad. So the integral from 3 to infinity of 3 over x squared minus x. All I've done is change this number and this number from 2's to 3's. So here's what I want you to be thinking. I can think of this as essentially, so basically, when I'm looking at a rational function and it's an improper integral, I'm kind of thinking of the highest powers of x. So this 3 over x squared minus x, when I see that, what I really actually see is, oh, that looks like 1 over x squared. The highest power of x in the numerator, I don't have any, so I just got a 1 or a 3, which fine. The highest power of x in the bottom is x squared. And I know that the integral of 1 over x squared from 1 to infinity converges. So I am pretty confident, without actually doing anything yet, that this is a convergent improper integral, because it looks enough like 1 over x squared. Now, there's a lot more work to this because, and again, I will point out that on this discussion sheet, he does say to evaluate. So you could, it would be difficult to show that this converged by the comparison test, because you have to say that this was less than something that was convergent. But when you subtract from the denominator, you're making the denominator smaller, which makes the fraction bigger. So it's hard to show this is less than something. That's okay. So it's good to have an idea of what happens. We think, oh, this probably converges. So let's go ahead and see, how do we integrate that? I think it's in partial fractions. So let's do the integral off to the side. So 3 over x squared minus x is 3 over x times x minus 1, which I'm going to say is a over x plus b over x minus 1. Also, I suppose I could do one step here and say this is the limit as b goes to infinity of the integral from 3 to b of 3 over x times x minus 1. Okay. So then we're going to multiply both sides by this common denominator. So we're going to have 3 on the left, a times x minus 1 plus b times x on the right. So we're going to let x equal 1 and get 3 equal to b times 1. So b equals 3. And then we let x equal 0, and we get 3 equals a times negative 1. So a is negative 3. So then we know that we're going to be integrating, instead of 3 over x times x minus 1, we're going to be integrating negative 3 over x plus 3 over x minus 1, which is equal to negative 3 natural log of absolute value of x plus 3 natural log of absolute value of x minus 1. Any questions about this before we move on? I am going to write it as 3 natural log of x minus 1 minus 3 natural log of x divided by x. And I actually want to point out here that since we're between 3 and infinity, we can drop the absolute values since the insides are never going to be negative. I'm going to erase this because I want to still use what I've got here. So here it goes. Last chance for questions. All right. Again, remember, we said our intuition was that this thing converged. We're not wrong. This thing does converge. But this one's a little bit tricky. So this is going to become the limit as b goes to infinity of the integral of this, which is that, 3 natural log of x minus 1 minus 3 natural log of x from 3 to b. Okay, now plugging in my limits of integration, make the limit as b goes to infinity of 3 natural log of b minus 1 minus 3 natural log of b minus 3 natural log of 3 minus 1, which is 2, minus 3 natural log of 3. Okay, so let me ask you guys, and it's okay to say what you, just answer the question. As b goes to, and I would like an answer, please. As b goes to infinity, what happens to 3 natural log of b minus 1? Does this converge to some number, or does this go to infinity?
Does it go to infinity?
It does. And so it would be easy to make a mistake here and say that this thing diverged. It does not diverge, but it's very, very easy to be like, oh, well, I've got infinity here, it's divergent, I'm done. But the problem here is that's not exactly true, because what we actually have is we have infinity minus infinity, which I know I've said if you have if you have one integral that's infinity minus another integral that's infinity, you just say the whole thing diverges. But that's not what we actually have, right? We've done the one integral, and we've gotten to a point where the limit is a limit that's an infinity minus infinity type. And when you have an infinity minus infinity type, that's an indeterminate form. You have to do something. Sometimes it involves L'Hopital's rule. We don't need to use L'Hopital's rule here. What we do need to use is the fact that we can combine these natural logs. So I can factor out, in fact, I can factor out a 3 from the whole damn thing. This is equal to 3 times the limit as b goes to infinity of the natural log of b minus 1 minus the natural log of b minus natural log of 2 minus natural log of 3. And we can combine this as one logarithm. We can write this as 3 times the limit as b goes to infinity of the natural log of b minus 1 divided by b. Minus, let's go ahead and combine this too. This is minus, no, it's not, minus natural log of 2 plus natural log of 3. Okay, now, even if you don't think you know it, you actually know it. Everybody knows what the limit as b goes to infinity of b minus 1 over b is. Can anybody tell me what it is? Let me ask you guys a different question. Type in the chat or say it. What's the limit as x goes to infinity of 2x squared plus 5 over 3x squared plus x plus 7? Somebody please tell me. What's that?
Oh, well, for the one you just did, it would be 2/3.
Right. Because we know this rule that when you have a limit to infinity of a rational function, where the degree on top and the degree on the bottom are the same, the limit is the quotient or fraction of those leading coefficients. Okay, that's exactly the situation we have here. We have a rational function, degree on top is 1, degree on the bottom is 1, and the limit is the quotient of those leading coefficients, which is 1 over 1. So this ends up being 3 times the natural log of 1, which is 0, plus the natural log of 3 minus the natural log of 2. That's 0, and you could combine these as the natural log of 3/2. So this would equal 3 times the natural log of 3/2. More importantly, this would be convergent. So this integral, as we predicted, is a convergent integral. Kind of cool. So I will tell you before you just one sec. This is a question teachers love to ask. Because it's challenging, but it's not impossible. So when you see something, again, if you see something where it's like a 1 over x squared, you should be thinking it's going to converge. Now, it's probably going to be partial fractions, and when you break it up, you're probably going to get a logarithm minus another logarithm, and the key is to combine those logarithms. Before you can combine them, though, you have to basically the coefficients have to be the same. If the coefficients are different, it's a little bit more challenging. But yeah. So someone had a question though?
Yeah, I was gonna say we deduced that it was gonna converge because of we compared our original integral to the integral of 1 over x squared.
1 over x squared.
Yeah.
Yeah.
Oh, okay then. Sounds good. Thank you, Jim.
I said this looks enough like 1 over x squared that I'm pretty sure it converges. Because so let me show you another example of what I mean by this. Let's say we were going to do the integral from 1 to infinity of, I don't know, 5x squared plus 2x plus 1 over x to the 5th plus 3x plus 9. We're not actually going to do it, but here's what I'm going to tell you. I know this integral converges, and I know it converges because the function is essentially, I don't care about anything but the highest power of x and the highest power of x. This is essentially x squared over x to the 5th, which is 1 over x cubed. And I know that the integral of 1 over x cubed from 1 to infinity is convergent. This is also convergent. Now, it's a little bit harder to show that this is less than 1 over x cubed because it's probably actually not. This requires a test that's called the limit comparison test, which again, I don't think we want to talk about unless we have to. But what I will tell you is for rational-ish functions, you can always, if it's just powers of x, right? You can always do this thing where you're just saying, okay, I'm going to compare powers, and if the power on the bottom is bigger than 1, I'm thinking it's going to converge. If the power on the bottom is less than 1, I'm thinking it's less than or equal to 1, I'm thinking it's going to diverge. So another example would be something like this. So this converges. Again, we're not going to show it, but you can look at something like this. Sure. The integral from 2 to infinity of x squared plus 3x over the square root of, sure, x cubed plus x cubed minus 1. Minus 1? Yeah, minus 1 is safe. Yeah, sure. We did the problem kind of like this at the beginning-ish, but that one we were able to do a u sub 4. And this one you can't do a u sub 4 because if you let u equal x cubed, your du is 3x squared, but you still have this leftover 3x to deal with. Here's what I can say. I can say this is essentially acting like x squared on top. And what's the biggest power of x on the bottom? It might not be super straightforwardly obvious. It's not x cubed. It's x to the what?
Would it be x to the 3 halves?
Right, exactly, because it's x to the 3rd to the 1/2 power because of the square root. And x squared over x to the 3 halves is 1 over x to the 1/2. And that power is less than or equal to 1. So I'm pretty sure this is divergent. And actually, we can show this one is. Let me show you. So it is true that x squared plus 3x. Actually, let me start here. Let me start with this. X cubed minus 1 is less than x cubed. Check. When you take the reciprocal of both sides, you change the order of the inequality. Check. Square rooting both sides doesn't change the inequality as long as everything's always positive. And since we're between 2 and infinity, all these things are positive. So you can slap on a square root there and still be safe. And then it's also true that x squared plus 3x is bigger than x squared. So this is bigger than this, and this is bigger than this. If you multiply these together, it's going to be bigger than if you multiply these together. So x squared plus 3x times 1 over the square root of x cubed minus 1 is bigger than x squared over the square root of x cubed. Oh yeah, that's fine. That's fine. I messed this up. I didn't mess it up. I just made it not quite exactly what I wanted, but that's all right. So then the integral of this is definitely bigger than what I really wanted. Yeah, I wanted to make this a 5 here. I'm gonna make it a 5 just to show you guys what I really wanted. Sorry. Okay, my 3s look enough like 5s anyways. It's not a big difference. So then this is 1, right? When I said something over here before like this, I said that was 1 over x to the 1/2. That was incorrect. This is just x to the 1/2, which is clearly divergent. This is 1 over x to the 1/2, which is still divergent. So since this integral is bigger than that integral, which is equal to that integral, and this integral is divergent, we can say by direct comparison, this integral diverges. But again, I'm starting with the intuition of the highest power on top, x squared, over the highest power on the bottom, which here looks like x to the 5/2. And that reduces to 1 over x to the 1/2, actually, which is divergent. So that's the intuition I'm using when I have these integrals that can't actually be integrated. Let's look at a couple more that people ask me from this Morris handout because they are tricky. So, so this next one, no, this next one's fine. So I want to ask everybody. I think there's a way. I wonder. Let me do one thing here. I'm curious. There's a way to like make it so the chat is only private. Oh yeah. Or for a moment, I'm going to make it so you can only chat with me. So try sending me a message, anything right now. Can I see things? Yep. So all your messages are coming up as private. Cool. Yes. Awesome. So let me ask you guys. I want to know what your intuition is for this integral, which is definitely one of the ones on Morris's handout. The integral of dx over x plus 1 times x squared plus 1 from 0 to infinity. Is your intuition that this is convergent or divergent? Throw it at me. And you can just type a C or a D. C for convergent, D for divergent. I want to see all your responses. Keep them coming, keep them coming. There's still a lot more of you. I need at least 3 more responses. It's okay to guess. It's okay to be wrong. We don't learn if we're not wrong sometimes. You can't write it again, right? I know it's still you. One more person. What do you think? Converge, diverge, converge, diverge. I can wait all day. I mean, I can't really. I can wait for 19 minutes if it's possible. I wouldn't do that, but nobody else is going to respond. All right. So my intuition here is this is convergent because if I multiply out the bottom, I don't actually want to multiply it out. If I multiply out the bottom, I've got, let's actually write it as a 1 on top. I've got 1 over x times x squared is x cubed plus smaller powers of x. So this is acting like a 1 over x cubed, which is convergent from, as long as it's not undefined anywhere, which it's not, because right, x plus 1 is always positive between 0 and infinity, and x squared plus 1 is always positive between 0 and infinity. So this is never going to be undefined in some weird way. Like if this was an x minus 1, we'd have some other issues to deal with, but we don't. So this one's definitely looking like it's probably going to converge. That's our intuition. Great. It's important and it's useful to have a good idea about what you think is going to happen before you actually start going. On the other hand, so I would point out this intuition is really only valid when you have infinity. Like if I asked you, on the other hand, about the integral from like -1 to 0 of dx over x plus 1 times x squared plus 1, this does not converge. This integral actually, I'm pretty sure, diverges. So this intuition we've been talking about like looking at and comparing it to 1 over x to the p, where the power has to be larger than 1 to converge and smaller than or equal to 1 to diverge. It's only true for integrals where you have infinity as your only kind of problem.
James,
Yeah.
would this type of intuition also work with like if we have negative infinity?
Yes. It also works for a negative infinity.
Oh, but what if we had both negative infinity and infinity as our limits of
It
integration?
still should work as long as it's not undefined somewhere in the middle, which they
Okay.
often are, right? Like for example, if you have the integral from 1 over x squared from negative infinity to infinity, that's going to diverge because at 0 it's going to diverge.
Mhm.
On the other hand, this integral from negative infinity to infinity of 1 over x squared plus 1, that integral converges because you no longer have an undefined point somewhere in the middle, and it's acting like 1 over x squared.
Okay, yeah, that makes sense.
This integral here is what's to do. So we know that the integral of 1 over x squared plus 1 is the arctangent of x. And then this is very, very wrong to write, but it's essentially this, right? Really, it's the limit as b goes to infinity of the arctangent of b minus the arctangent of 0. Right, that's half of it. And then the other one is plus the limit as a goes to minus infinity of the arctangent of 0 minus the arctangent of a. And then here's a good question. What's the limit as b goes to infinity of the arctangent of b?
B and E. Oh, pi over 2.
And the way we know this is by thinking about the arctangent graph. Right? The tangent graph has vertical asymptotes at pi over 2 and negative pi over 2. The arctangent graph has horizontal asymptotes at pi over 2 and negative pi over 2. It looks like this. So that part's pi over 2, that part's 0, that part's 0, and that part's negative pi over 2. So you end up getting pi. So the integral from negative infinity to infinity of 1 over x squared plus 1 is pi. Kind of neat. But that wasn't the question we started with. The question we started with was this lovely looking thing, which we're pretty sure converges. But what method of integration are we going to have to use? Hint, the bottom's already factored.
Partial fractions.
Yeah. And I'm going to turn back on the you can chat with everybody. Okay, now you can chat with everyone again if you want to. All right, so partial fractions. So we have 1 over x plus 1 times x squared plus 1 equal to a over x plus 1 plus bx plus c over x squared plus 1. Good times. Not good times. Okay. This one, yeah. So do the usual thing, multiply both sides by the common denominator. You're going to get 1 on the left equal to a times x squared plus 1 plus bx plus c times x. All right. So then we have to well, we don't have to, but we're going to use a convenient value of x. Like x equal to 0. Then x equal to 0, then you get 1 on the left. You get a times 0 plus 1 plus b times 0 plus c all times 0, so that's just 0. So you get a equal to 1. Okay. And then we have no more convenient values of x. So we're going to do the other thing where we equate coefficients. Let's look at x squared. On the left, there is 0x squared. On the right, there is an a times x squared. And there is a b times x squared. So since a is 1, a plus b equals 0, b has to equal negative a, which is negative 1. Let's look at the coefficient of x. On the left, there is 0x. On the right, there is not an a times x. There's not a b times x, there's the b times x squared, but there is a c times x. So c has to be 0. Okay. So this ends up equaling 1 over x plus 1 minus x over x squared plus 1. All right. Yeah, cool. Yeah. X squared plus 1 minus. I feel like I'm making a mistake somewhere. Let's double check. X squared plus 1. That's right. Minus x squared. X squared plus 1. Now that seems right. I just feel like I'm going to multiply these back out. I'm not getting that. X squared plus 1 minus x times x plus 1. I feel like I'm doing something dumb and I'm not seeing it. Sorry, it's just I want to check my work. So let's see, if I multiply this out, I get x squared plus 1 minus x squared minus x. And that's definitely not what we started with on top. What's going on here? What kind of silly mistake am I making? Let's check it out. So, so I definitely did make a mistake, and I see it now. Do you guys see the mistake I made? I'll tell you, it's right here. I forgot, or when I multiply. So this is why it's really important to remember what you're doing. So first of all, how did I say I made a mistake? I don't actually know how I saw I made a mistake, but for some reason I decided to check. And I noticed that if you actually subtract these fractions together, you get x squared plus 1 minus x times x plus 1, which is x squared plus 1 minus x squared minus x. And I definitely don't have 1 minus x on top. I just have 1 on top. That was problematic. And the issue I made was when I multiply both sides, I have a common denominator here. Right, so this and this times x plus 1 times x squared plus 1. On the left, that was fine. For a, I was fine. Right? I canceled the x plus 1s. For bx plus c, I canceled the x squared plus 1, but I should have been left with an x plus 1, and I wasn't. I made an error there for sure. So let's do this all over again. So my convenient value actually isn't 0, it's negative 1. So if x is negative 1, we get 1 on the left, we get a times 2 on the right, and then bx plus c times 0. So a is 1/2. And then we're out of convenient values, so let's do the equating coefficients. So for x squared, 0 x squared on the left, you still have an a plus b. So b is negative 1/2. And then for x, you have 0x on the left, and it looks like you have a 0x there, or no x is there. You do have a bx times 1, and you do have a cx. So x is equal, or 0 is equal to b plus c. Since b is negative 1/2, c has to be positive 1/2. Okay, that looks a little bit more for it. So what we're actually integrating is the integral from 0 to infinity of 1/2 over x plus 1 plus negative 1/2 x over x plus 1 plus 1/2, oh, sorry, over x squared plus 1 plus 1/2 over x squared plus 1. Whew. Okay, so I kind of want to get to the other problem, and I know we're almost out of time. So I'm gonna talk this through real. Yeah, fine, I can do this. So I'm gonna erase. So here's what we've got. We've got the limit as b goes to infinity of, I'm going to factor out the 1/2 because there's a 1/2 on all of them. So the 1/2 times the integral from 0 to b of 1 over x plus 1 minus x over x squared plus 1 plus 1/2 over x squared plus 1. Sorry, not 1/2. I factored out the 1/2, which is the 1. I guess you don't really need this bracket here. Okay, so then we're going to integrate. You get the limit as b goes to infinity of 1/2 times the integral of that is the natural log of the absolute value of x plus 1. Okay, x over x squared plus 1. The integral is going to be 1/2 times the natural log of the absolute value of x squared plus 1. Because the derivative of that is 1 over x squared plus 1 times 2x. So you get 1/2 times 2x, which gives you your x over x squared plus 1. And then the integral of 1 over x squared plus 1 is the arc tangent of x from 0 to b. Right. So then we do the limit as b goes to infinity of 1/2 times the natural log of b plus 1. What minus? Okay, this is good. This is a hard problem. Minus 1/2 the natural log of b squared plus 1 plus the arc tangent of b minus, when you plug in 0, you get the natural log of 1, which is 0, minus the natural log of 1, which is 0, plus the arc tangent of 0, which is 0. So it's all zeros, but it's important to check. Okay, so this is actually the tricky situation I was kind of alluding to earlier, where if your logarithms don't have the same power or the same coefficient, you can't just jam them together. So before you can stick this and this together, you have to bring this 1/2 up as the power. So this expression here becomes the natural log of b plus 1 on top, and the b squared plus 1 to the 1/2 power, or the square root of b squared plus 1, plus the arc tangent of b. Morris is asking you guys some tough questions here. Okay, so let me ask you guys, what's the limit as b goes to infinity of b plus 1 over the square root of b squared plus 1? Well, we don't have a lot of time.
It'd just be 1.
It'd just be 1. Because essentially you have b over b.
Yeah.
So that's going to be the natural log of 1, which is 0. And as b goes to infinity, we just saw before that the arc tangent of b goes to pi over 2. So this ends up being 1/2 times pi over 2, which is pi over 4. It's a tough problem. It's a good problem. Like, it's definitely bringing in like all the pieces you could possibly see, but There's a lot of things to unpack there for sure. All right, let me just briefly, we don't have enough time to do the last problem, but let me just talk about it real quick. The last problem that someone asked me, which is also, I think, tricky. So, the problem somebody asked me was this one. The integral, yeah, it's the last Morris one. The integral from 2 to infinity. Although someone wrote 0 to infinity, but I think they meant 2 to infinity, because if it's 0, it's a different ball of wax over 1 plus x times the square root of x. And my intuition here is that this converges, because again, my highest power of x on the top, I don't have any x, so it's 1. And the highest power of x on the bottom, I have an x to the 3 halves. So this is looking like the integral of 1 over x to the 3 halves, which I know converges. Okay, so I'm pretty sure it converges. How do we get there? We do a u sub. So this is a tricky problem. We're going to let u equal the square root of x. Your du is going to be 1 over 2 root x dx. So 2 du is equal to dx over the square root of x, which I have right there. So the integral of dx over 1 plus x times the square root of x is going to be, there's my du, and then what's left? 1 plus what? What's x equal to? Let me ask you again. What's x equal to?
U squared.
Right. Oh, we know how to integrate that. That's the arc tangent of u, which is the arc tangent of the square root of x. So then you can do the whole limit thing. Say, okay, this is going to be the limit as b goes to infinity of the integral from 2 to b of dx over 1 plus x times the square root of x. And then you can just be like, that's going to equal the limit as b goes to infinity of, well, we know the integral of that is exactly the arctangent of the square root of x. From to, wow, this is a missed opportunity here. I'll mention why. So from 2 to infinity, sorry, from 2 to b. You really should have made that a 3. It would have been such a cool, it would have been so much of a cooler problem if that was a 3 than a 2. Here's why. Unless I made a mistake. I don't think I made a mistake, but clearly you guys know I make mistakes. I do all the time. So you get the limit as b goes to infinity of the arctangent of the square root of b minus the arctangent of the square root of 2. As b goes to infinity, square root of b goes to infinity, and the arctangent of infinity is once again what? Pi over 2. And if you just made that a square root of 3, right? If you just made that a 3 instead of a 2, the arctangent of the square root of 3 is, the arctangent of the square root of 3 is pi over 3. It would have been so cool. Arctangent of the square root of 2 is some other angle that's not a nice pi over 3 or pi over 6 or pi over 4. That's too bad. We're doing awesome doing that. Again, unless I made some really dumb mistake, now I'm like, maybe I made a mistake because the other problem was so cool. I don't think I made a mistake though, right? U is the square root of x. Du is 1 over 2 root x dx. We've got that 2 du. That's that for sure. And then this becomes, there's your, I did forget the 2. Right? I lost my 2 along the way. So there should have been a 2 here. Apologies. So there should have been a 2 here, a 2 here, a 2 here, a 2 times all of this. So your final answer should be 2 times pi over 2 minus the arctangent of root 2. But the arctangent of root 2 still is not a nice number, so nothing you can do about that.